January 15, 1944. Westward Ho Beach, Devon, England. Admiral Lord Louis Mountbatten steadies his binoculars against the Atlantic wind as engineers complete final checks on the most unconventional weapon he has ever been asked to approve for D-Day operations. The device before him stands 10 feet tall, two massive wooden wheels connected by a central cylindrical drum. 70 cordite rockets bristle from the rim of each wheel like the spines of some mechanical beast. The drum between them contains 4,000 pounds of high explosives, enough to obliterate a concrete bunker or create a crater 30 feet across. The engineers from the Directorate of Miscellaneous Weapons Development assure him it will roll up the beaches of Normandy at 60 miles per hour, smash through Hitler's Atlantic Wall, and revolutionize amphibious assault. This cannot possibly work as advertised. No weapon this crude could function reliably in combat. But Mountbatten has learned not to dismiss British ingenuity too quickly. The beach obstacle clearance problem remains unsolved. The Atlantic Wall presents 15,000 concrete fortifications along the French coast, many positioned to enfilade landing beaches with interlocking fields of fire. Conventional naval bombardment has proven insufficient against reinforced bunkers. Tank-delivered demolitions require vehicles to survive beach obstacles and reach defensive positions. The Americans have their specialized armor, Sherman crabs with flails, Churchill crocodile flame tanks, but nothing addresses the fundamental problem of how to destroy fortifications in the critical first minutes when assault troops are most vulnerable. Lieutenant Nevil Shute Norway stands 200 yards down the beach, clipboard in hand, calculations racing through his mind. 18 months of development have led to this moment. The guidance cables are secured. The ignition sequence is verified. First Sea Lord Admiral Sir Dudley Pound watches from the observation stand with other combined operations brass. The Panjandrum, named mockingly after a nonsense poem about a pompous grand Panjandrum, represents the culmination of every unconventional warfare experiment the Admiralty's most creative minds could conceive. The chief engineer signals ready. Norway gives the order. The rockets ignite with a sound like tearing canvas amplified 100 times. Smoke erupts in white plumes from 140 ignition points. The Panjandrum lurches forward, gathering speed. The wheels beginning their designed rotation. Propulsion and motion finally synchronized after months of failed attempts. For exactly 8 seconds, everything works perfectly. Then the first rocket detaches from the left wheel, spinning wildly into the air, trailing smoke. Then another, then 6 more in rapid succession. The Panjandrum veers sharply right, guidance cables snapping like thread. The remaining rockets continue firing, but the asymmetric thrust sends the device into a chaotic spiral. It bounces over sand ridges, changes direction seemingly at random, and accelerates directly toward the observation stands. Admiral Mountbatten and the assembled brass run for their lives as Britain's newest secret weapon, carrying 1 ton of high explosives and 60 still firing rockets, bears down on them at 40 miles per hour with no guidance system, no kill switch, and no way to stop. The journey to this catastrophic demonstration had begun 25 months earlier in the cold logic of military necessity. January 1943. The Allied High Command faced a seemingly insurmountable obstacle. Operation Overlord, the planned invasion of occupied France, required landing hundreds of thousands of troops on beaches defended by the most formidable coastal fortification system ever constructed. Hitler's Atlantic Wall stretched from Norway to the Spanish border, consuming 17 million cubic meters of concrete and employing 1.2 million workers at peak construction. Intelligence estimates indicated 15,000 defensive positions, including steel-reinforced bunkers with walls up to 3 meters thick, capable of withstanding direct hits from battleship shells. The Dieppe raid of August 19, 1942, had demonstrated with brutal clarity the consequences of assaulting prepared positions without adequate means to eliminate beach defenses. Of the 6,086 men who went ashore, primarily Canadian troops, 3,623 became casualties within 9 hours. German defensive positions remained largely intact despite naval gunfire support. British and Canadian assault engineers lacked mobile, rapidly deployable explosive systems capable of breaching concrete fortifications while under fire. The tanks that made it ashore became trapped by beach obstacles or destroyed by anti-tank guns positioned in protected emplacements. Major Millis Jeffress, head of the Ministry of Supply's Experimental Weapons Division, convened a meeting at the War Office in late December 1942. Present were representatives from the Admiralty's Directorate of Miscellaneous Weapons Development, Combined Operations Experimental Establishment at Leytonstone, and several civilian engineers recruited for their creative thinking. The brief was simple and, apparently, impossible. Develop a system to deliver large explosive charges against beach fortifications within the first wave of assault without requiring troops to approach under fire and without depending on specialized armored vehicles that might bog down or be destroyed crossing the beach. Lieutenant Nevil Shute, Norway, a civilian engineer and novelist working in naval weapons development, proposed the concept that would become the Panjandrum. Norway had previously designed the R-100 and possessed an engineer's appreciation for unconventional solutions. His logic was mechanically sound. Wheels could traverse soft sand better than tracks or legs. Rocket propulsion required no vulnerable power plant or transmission. Self-propelled delivery eliminated the need for operators to approach enemy positions. A simple, robust design using available materials could be manufactured quickly without straining industrial capacity. The Directorate approved initial development funding of £3,000 in January 1943. Norway and his team at the Combined Operations Experimental Establishment began design work immediately. The concept called for 2 wheels, each 10 feet in diameter, constructed from a steel framework covered with wooden planking. Between them, a cylindrical drum would hold the explosive payload. Initially calculated at £2,000, later increased to £4,000 after consultations with demolitions experts regarding concrete penetration requirements. Cordite rockets, the same type used for jet-assisted takeoff on aircraft, would be mounted around the rim of each wheel, providing both forward thrust and rotational momentum. The mathematics appeared straightforward. 70 rockets per wheel, each generating 5 pounds of thrust for 12 seconds, would produce 700 pounds of total force. At a target weight of 1,500 pounds per wheel, plus 4,000 pounds for the explosive drum, total 7,000 pounds, the thrust-to-weight ratio would theoretically produce acceleration sufficient to reach 60 miles per hour within 300 yards, the average depth of French invasion beaches from waterline to defensive positions. The wheel's circumference of 31.4 feet meant each complete rotation would advance the device that distance. At 60 miles per hour, the Panjandrum would make approximately 167 rotations per minute, a rotational speed well within the structural tolerances of the wheel framework. Construction of the first prototype began in April 1943. Norway's team fabricated the wheels from steel tubing with wooden rim segments, keeping weight low while maintaining structural rigidity. The explosive drum used welded steel construction with attachment points for standardized demolitions charges. Rocket mounting brackets were positioned to allow synchronized ignition through an electrical firing system. By late August 1943, the first full-scale Panjandrum stood ready for testing. September 7, 1943, marked the weapon's debut. Norway's team transported the device to Westward Ho beach in Devon, selected for its similarity to Normandy beach profiles and its remoteness from civilian observation. Captain Brian Legg Kennett, chief engineer for the trials, supervised assembly of the test unit. The initial run carried no explosive payload. The drum contained sandbags weighing 2,000 pounds to simulate half the intended charge. 40 rockets per wheel provided propulsion, half the planned number, allowing incremental testing of the propulsion system. At 2:15 in the afternoon, observers positioned 500 yards from the launch point, Kennett initiated the firing sequence. The rockets ignited successfully, producing tremendous smoke and noise. The Panjandrum began to roll forward. For approximately 50 yards, the device performed as designed, tracking straight up the beach at an estimated 35 miles per hour. Then the first rocket burned through its propellant, creating asymmetric thrust. The device veered left. 3 seconds later, 6 more rockets exhausted simultaneously, sending the Panjandrum into a lateral skid that ended with both wheels digging into soft sand. The rockets continued burning, spinning the embedded wheels uselessly until propellant exhaustion. Norway's engineering team immediately identified the core problem. The cordite rockets, designed for aircraft-assisted takeoff, burned for only 12 seconds but did not all ignite or exhaust simultaneously, despite electrical triggering. Variations in individual rocket manufacturing, mounting angle, or exposure to moisture created ignition delays of up to 2 seconds and burn time variations of 1 second or more. In aircraft use, these variations were negligible. For a ground vehicle requiring balanced thrust between 2 independent wheels, millisecond timing differences produced catastrophic directional instability. The team spent the next 3 months attempting solutions. They tried longer burning rockets with lower thrust. They experimented with progressive ignition sequences, lighting rockets in stages rather than all at once. They added weighted guidance mechanisms and deployed restraining cables. Each modification created new problems. Longer rockets increased weight and reduced thrust-to-weight ratio. Progressive ignition reduced acceleration but introduced even more complex timing variables. Guidance weights threw off rotational balance. Cables broke or tangled. By December 1943, Norway's team had conducted 17 test runs, with only 2 achieving reasonably stable trajectories, both traveling less than 100 yards before veering off course. Pressure from Combined Operations Headquarters intensified. D-Day planning was accelerating. The beach obstacle problem remained unsolved. Senior commanders needed to see the Panjandrum demonstrate combat viability. A full-scale demonstration was scheduled for January 15, 1944, with attendance mandatory for all key decision-makers, including Mountbatten, Pound, and the Combined Operations staff. Norway's team had exactly 6 weeks to make the Panjandrum controllable. Through late December 1943 and early January 1944, the pattern of failure repeated with mechanical consistency. Test Run 18, December 22, 1943. The Panjandrum achieved 45 yards of stable travel before 8 rockets detached simultaneously from the left wheel, sending the device into a spinning tumble that required 2 hours to extract from packed sand. Test Run 19, December 29, 1943. New rocket mounting brackets reduced detachment risk but increased wheel weight. The device achieved only 25 miles per hour maximum velocity, insufficient to overcome beach obstacles or maintain momentum up sloped sand. Test Run 20, January 4, 1944. Reverting to original mounting design with reinforced attachment points, the Panjandrum rolled 80 yards, the longest successful run yet, before directional instability sent it careening in a wide circle, eventually colliding with and destroying an observation post positioned 300 yards from the intended trajectory. Test Run 21, January 7, 1944. The team added steel guide rails along the central drum to stabilize lateral movement. The additional 200 pounds reduced acceleration substantially. The device never exceeded 15 miles per hour and stopped entirely after 40 yards when thrust proved insufficient to maintain motion against rolling resistance. Test Run 22, January 10, 1944. Removing the guide rails but adding asymmetric rocket loading, 75 on the heavier left wheel, 65 on the lighter right wheel, the Panjandrum achieved 90 yards of relatively straight travel. Then rockets began detaching in groups of 3 and 4, transformed into unguided projectiles that spiraled across the beach. One rocket flew 200 yards before impacting harmlessly in surf. Another embedded itself in a wooden observation platform, failing to detach its spent casing and continuing to smolder until engineers extinguished it. Each failure illuminated the fundamental engineering trap Norway had walked into. The Panjandrum required 3 simultaneous conditions: symmetric thrust between wheels, sustained rotational velocity, and stable directional tracking. Achieving any 2 proved possible. Achieving all 3 proved impossible with available materials and propulsion technology. Symmetric thrust required perfectly manufactured rockets with identical burn rates, impossible given wartime production tolerances. Sustained velocity required continuous power, but cordite rockets were by nature short-duration devices. Stable tracking required either aerodynamic control surfaces, useless on a ground device, or active guidance, which would require operators or remote control systems that didn't yet exist with sufficient reliability. The physics offered no compromise. Every pound added for stability reduced acceleration. Every reduction in rocket number extended burn time but decreased peak velocity. Every attempt to improve guidance created new mechanical complexity that failed in testing. Norway had designed a weapon that existed in theoretical possibility but defied practical implementation. Colonel E.S. Harrison, Combined Operations Observer assigned to evaluate Panjandrum testing, filed his interim report on January 12, 1944. His assessment was clinical. The device demonstrates potential as a beach assault weapon if directional control can be achieved. However, current failure rate of 92% in controlled testing suggests extreme risk if deployed in combat conditions where uncontrolled device could threaten friendly forces. Recommend additional development time or alternative approaches to beach obstacle clearance problem. But time had run out. The January 15 demonstration could not be postponed. Mountbatten and the Combined Operations leadership needed to make final decisions on D-Day assault equipment. Production schedules required immediate commitment to manufacturing. If the Panjandrum was to see Normandy, it needed approval within days. Norway's team prepared for the demonstration with the desperation of engineers who knew their creation wasn't ready but had no choice except to proceed. They selected the test unit with the straightest previous run, Test 20's device, repaired after its collision with the observation post. They installed fresh rockets, each individually tested for ignition reliability. They positioned guide cables at 100-yard intervals anchored to steel stakes driven 3 feet into sand. They mapped every yard of the test beach, removing rocks and leveling sand to create the most favorable possible conditions.
The team positioned observation stands 400 yards from the launch point behind reinforced blast barriers. They established a secondary observation position 800 yards distant for photography and technical assessment.
They briefed Admiral Mountbatten, Admiral Pound, Rear Admiral Charles Hughes Hallett, and 15 other senior officers on what to expect. Initial acceleration, stable travel for approximately 100 to 150 yards, guide cables providing directional correction, deceleration as rockets exhausted, and final positioning against a simulated bunker target consisting of stacked concrete blocks. What they did not brief, because they did not know, was what would happen when guide cables designed for 35 miles per hour speeds encountered a device traveling 45 miles per hour with asymmetric thrust producing lateral force equivalent to 200 pounds. The mathematics of tensile strength versus momentum were about to provide the answer. January 15, 1944. 2:45 in the afternoon. The wind off the Atlantic carries salt spray across Westward Ho Beach as Captain Brian Kennett makes final ignition checks. The Panjandrum stands ready, 70 rockets per wheel mounted in the most precise alignment Norway's team has ever achieved. The explosive drum contains 4,000 pounds of inert material, concrete blocks mixed with sand to simulate the exact weight distribution of high explosives. This will be the first test at full combat weight. The device tips the scales at 8,400 pounds total, 1,400 pounds heavier than previous trials. Admiral Mountbatten watches through binoculars from the primary observation stand. Beside him, First Sea Lord Admiral Sir Dudley Pound discusses timetables for D-Day equipment finalization with Rear Admiral Hughes Hallett. The consensus among the brass: approval today means production begins next week, 6 months to manufacture 200 units, sufficient for the first wave at 3 beaches. Rejection means back to conventional demolitions carried by engineers under fire. Kennett signals ready. Norway, positioned at the technical observation post with stopwatch and measurement equipment, calls for ignition. 140 rockets ignite within 1.3 seconds of each other, the best synchronization yet achieved. The sound is overwhelming, a sustained roar like a freight train accelerating inside a tunnel. White smoke erupts in a dense cloud that momentarily obscures the entire device. The Panjandrum lurches forward, wheels spinning, the massive frame shuddering as 700 pounds of thrust overcomes inertia. For the first 40 yards, Norway allows himself to believe they have succeeded. The device tracks straight, the wheels rotating in perfect synchronization, velocity building smoothly. 25 miles per hour, 35 miles per hour, 42 miles per hour. The guidance cables deploy from spools, maintaining light tension exactly as designed. At the 50-yard mark, 8 rockets on the left wheel exhaust their propellant simultaneously. The thrust differential, now 40 pounds favoring the right wheel, produces immediate lateral force. The Panjandrum begins veering left at 5 degrees per second. The guidance cables take up tension, correct the drift, bring the device back to center. Norway's calculations vindicated. The cables work. Then, at 65 yards, traveling at 44 miles per hour, 12 rockets on the right wheel detach from their mountings. The physics are instantaneous and catastrophic. The left wheel now produces 350 pounds of thrust. The right wheel produces 290 pounds. The differential of 60 pounds, applied to opposite sides of an 8,400-pound device traveling at 44 miles per hour, generates rotational torque that snaps the first guidance cable with a crack audible 200 yards away.
The Panjandrum slews violently right, now traveling at 40 degrees from its intended course. The second guidance cable engages, arresting the rotation briefly. Then it too fails, parting under load. The detached rockets spiral through the air like fireworks, trailing white smoke, impacting randomly across the beach. One embeds itself in sand 30 feet from the primary observation stand. Two more fly over the blast barriers, one passing within 10 feet of Admiral Pound's position. The device is now completely uncontrolled, still propelled by 110 burning rockets, traveling at 46 miles per hour in an arc that curves steadily toward the assembled observers. Lieutenant Commander James Hodges, bomb disposal officer observing from the photography position, later recalled, "We watched it come about, still accelerating, and realized simultaneously that it was heading directly for the stands. Mountbatten was already moving. He'd recognized the danger before any of us. The others followed. I saw generals running, flag officers running, engineers scattering in every direction. The Panjandrum just kept coming, smoke pouring from both wheels, that ungodly noise of the rockets. I thought for certain it would hit the barriers with 4,000 pounds of simulated explosives aboard. Even inert, the impact would have killed anyone nearby." The device covered the 400 yards from launch to observation stand in exactly 18 seconds. At 380 yards, 10 more rockets exhausted, producing another thrust differential that turned the Panjandrum sharply left. It missed the primary observation stand by 70 feet, passed through the position where Rear Admiral Hughes Hallett had been standing 8 seconds earlier, and continued across the beach in a wide, looping curve. At 440 yards from launch, now traveling roughly parallel to the waterline, the Panjandrum encountered a beach photographer's position.
News photographer Maurice Ambler, assigned to document the demonstration for the Ministry of Information, had stationed himself with his Labrador retriever near the photography observation post, believing himself safely distant from the test zone. The Panjandrum's chaotic trajectory brought it directly through his position at 38 miles per hour, with 85 rockets still firing. Ambler escaped by diving into a shallow depression in the sand. His dog was not fast enough. The massive wooden wheels struck the animal directly, killing it instantly, and continued forward without any detectable change in trajectory or velocity. For another 90 seconds, the Panjandrum careened across Westward Ho Beach in decreasing arcs as rockets exhausted in random sequence. It passed within 50 feet of the surf line. It climbed a sand dune, became briefly airborne, and crashed down with sufficient force to crack the central drum's welded seams. It spun in place for 20 seconds when one wheel dug into soft sand while the other continued rotating at full thrust. Finally, 620 yards from its launch point and 280 yards from its intended target, the last rocket sputtered out. The Panjandrum rolled forward another 30 feet on momentum alone, then stopped, smoking quietly in the January afternoon. The subsequent silence was total except for the wind and waves. Admiral Mountbatten returned to the observation stand, straightened his uniform, and turned to Norway. "Lieutenant, that demonstration has convinced me that the Panjandrum is indeed ready." Norway's face showed confusion. "Ready," Mountbatten continued, "to be photographed extensively, discussed loudly in every pub in Plymouth, and allowed to appear in as many intelligence reports as German reconnaissance can produce. It is completely combat ineffective and will never be deployed. But if Wehrmacht engineers spend the next 6 months designing obstacles to stop rocket wheels, they will not be designing obstacles to stop flail tanks and armored bulldozers. Project continuation approved. Testing will continue through June. Production planning will be discussed with appropriate industrial representatives. Thank you, gentlemen. That will be all." The Admiral walked to his staff car without looking back. Norway stood motionless on Westward Ho Beach, watching smoke still rising from his creation. Understanding that 18 months of engineering work had just been transformed from a combat weapon into a deception operation by executive decision, delivered while a dead dog lay 200 yards away. The Panjandrum had found its purpose, just not the one its designers intended. The requirements that created the Panjandrum originated in December 1942 at a combined operations planning conference addressing the Atlantic Wall problem. The specifications were precise. Deliver 2,000 to 4,000 pounds of high explosives against beach fortifications within 3 minutes of initial landing. Traverse 300 yards of beach, including soft sand, obstacles, and slopes up to 15 degrees. Function without requiring operators to approach enemy positions under fire. Utilize existing materials and propulsion systems to enable rapid production. Cost no more than 500 pounds per unit. Achieve 80% reliability in controlled testing before combat deployment consideration. The strategic context was equally clear. Operation Overlord would put 156,000 men ashore on June 6, 1944. Intelligence estimated German defensive positions could deliver sustained fire at 60 rounds per minute per position from ranges up to 1,200 yards. Every minute that beach fortifications remained operational would cost Allied casualties measured in dozens. The assault plan called for specialized armor to clear obstacles and suppress positions, but armor required time to wade ashore, organize, and advance. Infantry would be vulnerable for at least 10 minutes, 600 seconds, in which German gunners would have clear fields of fire. If unmanned explosive devices could destroy fortifications in the first wave, before armor arrived and before infantry concentrated, casualties could drop by 30 to 40%. The mathematics of saved lives justified enormous investment in any system that offered reliable obstacle clearance. Engineer Lieutenant Nevil Shute, Norway, accepted this mission with full understanding of its importance and its difficulty. Norway's background, designer of the R-100 airship, author of engineering-focused novels, veteran of materials science work, gave him unique perspective on what Churchill's scientific advisors called the problem of remote delivery. Rockets provided thrust, but no guidance. Tracks or wheels provided mobility but required operators. Explosives provided destructive power but needed precision placement. The impossible choice was immediately apparent. The mathematics were brutally simple. To traverse 300 yards of soft sand in 180 seconds required minimum sustained velocity of 30 miles per hour. At 8,000 pounds total weight, this demanded continuous thrust of at least 500 pounds to overcome rolling resistance, friction, and slope. Cordite rockets provided 5 pounds thrust for 12 seconds each. Therefore, minimum 100 rockets needed, arranged to maintain thrust throughout the run. But 100 rockets mounted on wheel rims created critical timing dependency. If rockets exhausted non-uniformly, thrust differentials would produce lateral force. A 50-pound thrust differential between left and right wheels acting through a 10-foot moment arm generated 500 foot-pounds of torque. At 8,000 pounds, this produced angular acceleration of approximately 0.06 radians per second squared, enough to turn the device 15 degrees off course in 5 seconds. Guidance systems offered no solution. Aerodynamic control surfaces required airflow, useless at ground level. Mechanical guidance required operators or remote control. Operators defeated the purpose, keeping men away from enemy fire. Remote control required radio frequency systems or cable controls. RF systems in 1943 lacked range, reliability, and resistance to jamming.
Cable controls needed cable strong enough to restrain 8,000 pounds traveling at 30 miles per hour. Steel cable of that strength weighed 4 pounds per foot, adding 1,200 pounds for 300 feet of cable, destroying the thrust-to-weight ratio. Norway chose rocket timing as the least intractable problem. He believed manufacturing tolerances could be tightened sufficiently to ensure rocket synchronization within acceptable margins. He believed testing would identify reliable ignition sequences. He believed engineering iteration would solve what physics made difficult but not impossible. This belief was not foolish. British engineering had solved apparently impossible problems throughout the war. Radar synchronized timing pulses across miles. Bomb sight computers calculated trajectories in real time. Cavity magnetron designs produced microwave radiation with precision previously unachievable. If rockets could be manufactured to tolerances of 0.5 seconds in 12-second burn time, just 4% variation, the Panjandrum would work. But cordite rocket manufacturing in wartime Britain operated under very different constraints than precision electronics. Rocket propellant composition varied with ambient temperature, humidity, and raw material quality. Wartime propellant supplies came from multiple manufacturers with different quality control standards. Storage conditions varied from climate-controlled magazines to damp beach depots. Each rocket underwent hand assembly by workers focused on output rather than precision timing. Testing individual rockets for burn rate required firing them, which destroyed them, making pre-selection impossible for actual deployment units. The 4% timing tolerance Norway needed was achievable under laboratory conditions, with selected propellant, controlled temperature, and extensive testing. It was completely unachievable in field conditions with production rockets. Norway discovered this through methodical elimination of alternatives. He tried progressive ignition, lighting inner rockets first, outer rockets last, creating sustained burn throughout the run. This required complex electrical timing circuits that failed in beach sand and salt spray. He tried mechanical governors to limit rotational velocity, preventing instability. The governors added weight and introduced mechanical complexity that broke under rocket acceleration forces. He tried weighted guidance arms extending from the central drum, using inertia to resist directional changes. The arms created aerodynamic drag and broke off when the device encountered obstacles. By December 1943, after 17 test runs and 8,000 pounds in development costs, Norway understood the Panjandrum suffered from a fundamental design philosophy error. He had attempted to create a precision device using imprecise components, to achieve reliable behavior from inherently unreliable systems, to control chaos through mechanical design alone. The choice had seemed reasonable in January 1943. The choice became clearly impossible by January 1944. But military necessity, production schedules, and command pressure meant Norway had to demonstrate the device anyway, knowing it would fail, hoping failure might somehow produce useful results. Admiral Mountbatten's reinterpretation of that failure, transforming the Panjandrum from combat weapon to deception tool, vindicated Norway's work in the most unexpected way possible. The device didn't need to work. It needed to be seen failing, extensively documented, and allowed to generate intelligence reports that would reach German planning staffs. A weapon that couldn't be controlled, accidentally, became a weapon that didn't need to be. The Panjandrum never killed a German soldier. Its consequences manifested in unexpected ways, documented in captured German intelligence reports and post-war analysis of Wehrmacht coastal defense preparation. Testing continued through June 1944, exactly as Mountbatten ordered.
February 18, 1944, Test Run 23 achieved 140 yards of stable travel before directional failure. March 3, 1944, Test 24 used 80 rockets per wheel, reduced payload to 3,000 pounds, achieved 180 yards but maximum velocity of only 22 miles per hour, inadequate for obstacle crossing. March 25, 1944, Test 25 returned to full specifications, traveled 95 yards, then veered sharply right and buried itself in a sand dune, requiring 3 hours of excavation and causing 400 pounds in damage to the test unit. British intelligence orchestrated careful leaks. Ministry of Information photographers documented tests from positions German reconnaissance flights regularly photographed. Technical specifications accidentally appeared in unclassified procurement documents routed through channels known to be compromised. Conversations in pubs near Plymouth and Devon, where combined operations personnel regularly drank, mentioned rocket wheels and beach rollers with enough specificity to ensure reports reached German intelligence through neutral contacts. The Abwehr, German military intelligence, took the bait completely. Oberkommando der Wehrmacht Coastal Defense Planning documents dated April 1944, captured after the war, contain explicit references to Britische Raketenradwaffen, British rocket wheel weapons. A technical assessment dated April 18, 1944, prepared by Wehrmacht engineers for Field Marshal Erwin Rommel's Army Group B, describes anticipated specifications. Diameter approximately 3 meters, weight estimated 3,500 to 4,000 kilograms. Explosive payload 1,500 to 2,000 kilograms. Propulsion via multiple rocket motors mounted on wheel circumference. Estimated velocity 80 to 100 kilometers per hour. Designed to traverse beach obstacles and destroy fortified positions through direct impact. The German estimates were remarkably accurate, except for velocity. Their intelligence overestimated by 30%, and they assumed the device worked reliably. Wehrmacht coastal engineers developed specific countermeasures. A directive dated May 2, 1944, ordered installation of Raketenradsperren, rocket wheel barriers, on beaches identified as likely invasion sites. These consisted of heavy logs embedded vertically in sand at 5-meter intervals, positioned to present rolling obstacles to wheel-based devices. Each barrier required 3 logs, each 4 meters long, driven 1.5 meters into sand, with upper portions angled seaward at 30 degrees. Construction records indicate Wehrmacht engineers installed approximately 2,800 of these specialized barriers along the Normandy coast between May 5 and June 5, 1944. Each barrier required approximately 40 man-hours of construction time. Total labor invested 112,000 man-hours. At average Wehrmacht engineering crew strength of 10 men per squad, this represented 11,200 squad days of effort, diverted from other defensive construction. Those 11,200 squad days could have built approximately 450 additional concrete bunkers using standard Wehrmacht fortification designs, or laid 15,000 anti-tank mines, or constructed 6,000 meters of anti-tank ditches. Instead, German engineers spent May 1944 preparing defenses against a weapon that had been secretly canceled, that had never worked reliably, and that was never going to appear on any invasion beach. The misdirection extended beyond physical obstacles. Wehrmacht tactical doctrine for beach defense, updated in May 1944, included specific instructions for engaging mobile explosive devices. Defenders were ordered to target the devices with anti-tank weapons at ranges beyond 200 meters before they could approach defensive positions. This guidance meant anti-tank guns would engage non-existent rocket wheels rather than actual Allied armor during the critical first minutes of assault.
On June 6, 1944, no Panjandrum rolled up Gold Beach, Juno Beach, or Sword Beach. British troops encountered the specialized anti-rocket wheel barriers at multiple locations. Assault engineers, unaware of the Panjandrum's existence or its role in German defensive planning, reported these obstacles as purpose unknown, possibly anti-vehicle barriers in after-action reports. The barriers proved largely ineffective against actual Allied tanks and specialized armor, though they did slow advance in several sectors and provided some cover for infantry. Post-war interviews with captured Wehrmacht coastal defense officers revealed the extent of German concern about British rocket weapons. Oberst Heinrich Schulze, commanding officer of the 716th Infantry Division, responsible for defending sectors of Normandy coastline, testified during interrogation in July 1944. We received intelligence reports beginning in March regarding British development of rocket-propelled explosive wheels. Army Group B engineering staff took these reports very seriously. We were ordered to prioritize construction of physical barriers and to prepare anti-tank engagement procedures. My officers questioned whether the intelligence was reliable. The weapons seemed technically improbable, but orders were explicit. We diverted construction resources from positions we judged more critical. The mathematics of operational security vindicated Mountbatten's decision. The Panjandrum project cost approximately £47,000 in total development and testing expenses from January 1943 through June 1944. German defensive preparation against Panjandrum attacks consumed an estimated £180,000 in materials and labor, based on Wehrmacht construction cost records. The return on investment? Nearly 4 to 1. Achieved entirely through accidental deception created by documenting genuine weapon development that happened to fail catastrophically. But the Panjandrum's consequences extended beyond resource misdirection. The device fundamentally demonstrated the gap between engineering ambition and practical capability, between theoretical effectiveness and operational reliability. Every military force in World War II developed weapons that looked magnificent in planning and failed miserably in testing. Most of these failures remained classified, hidden from historical record, their lessons unlearned. The Panjandrum failed publicly, spectacularly, and beneficially. The dog killed on Westward Ho Beach on January 15, 1944, the only documented casualty of Panjandrum testing, died because its owner stood too close to a weapon test, believing distance and barriers provided adequate safety. Maurice Ambler, the photographer, later wrote, "I thought I understood the danger zones. I positioned myself where the device could not possibly reach. I did not account for the weapon being completely uncontrolled. That failure of imagination cost my dog his life. It could easily have cost mine." This lesson, that unguided weapons threaten everyone equally, that control systems matter more than destructive power, that reliable mediocrity serves better than brilliant unpredictability, became encoded in British weapons development doctrine. Post-war analysis of experimental weapons programs shows a marked shift toward reliability testing earlier in development cycles, toward acceptance that some technical problems cannot be solved with available technology, toward willingness to cancel projects before they consume excessive resources. The Panjandrum's final test occurred on June 2, 1944, 4 days before D-Day. Test Run 32 used modified rocket mountings, reduced payload to 2,500 pounds, and employed the most carefully synchronized ignition system Norway's team had developed. The device achieved 220 yards of relatively stable travel, the best performance in 32 attempts, before thrust asymmetry produced the now familiar violent veer and loss of control. The test unit destroyed itself against a concrete test barrier, creating a crater 12 feet across and 4 feet deep. Had the explosive payload been live rather than simulated, the crater would have been 30 feet across and demolished the barrier completely. Norway filed his final report on June 8, 1944. The Panjandrum demonstrates adequate destructive capacity against concrete fortifications. Reliability remains at approximately 8% for stable travel exceeding 200 yards. This reliability rate is insufficient for combat deployment. Further development would require fundamental redesign of propulsion system, guidance mechanism, and structural framework. Estimated additional development time 18 to 24 months. Estimated additional cost £60,000 to £80,000. Recommendation: project termination. Alternative beach obstacle clearance methods demonstrate superior reliability. The Directorate of Miscellaneous Weapons Development accepted Norway's recommendation on June 15, 1944. The Panjandrum was officially cancelled. All test units were ordered destroyed to prevent capture and intelligence compromise. The program disappeared from official records, classified secret for the duration of the war and for 20 years afterward. But the physical evidence remained visible from the air. German reconnaissance photographs continued showing the specialized barriers along Normandy beaches. Wehrmacht engineers continued believing they had successfully defended against a British superweapon that never arrived.
The deception operation that Mountbatten conceived in 15 seconds of improvisation on Westward Ho Beach continued functioning through tactical surprise, resource misdirection, and enemy caution against a threat that existed only in planning documents and failed test videos. Production statistics for the Panjandrum tell a story of ambitious planning meeting engineering reality. Total units constructed: 13 full-scale prototypes between April 1943 and June 1944. 3 half-scale test units built in February 1943 for preliminary propulsion testing. 2 quarter-scale models used for structural analysis. Specifications varied across prototype versions. Mark I Panjandrum. Tests 1 through 8, September-November 1943. 10 feet diameter, 2,000 pounds explosive capacity, 40 rockets per wheel, wooden wheels with steel framework, central drum steel welded construction, estimated weight 6,200 pounds. Maximum recorded velocity 35 miles per hour. Longest stable run 80 yards. Mark II Panjandrum. Tests 9 through 17, November 1943, January 1944. 10 feet diameter, 3,000 pounds explosive capacity, 60 rockets per wheel, reinforced wooden wheels with steel bracing, modified drum with improved mounting system, estimated weight 7,400 pounds. Maximum recorded velocity 42 miles per hour. Longest stable run 95 yards. Mark III Panjandrum. Tests 18 through 32, January through June 1944. 10 feet diameter, 4,000 pounds explosive capacity, 70 rockets per wheel, steel reinforced wooden wheels with improved rocket mounting brackets, strengthened central drum with welded reinforcement, estimated weight 8,400 pounds. Maximum recorded velocity 46 miles per hour. Longest stable run 220 yards. Distribution of test outcomes across all 32 recorded trials. 3 tests achieved stable travel exceeding 150 yards, 9.4% success rate. 8 tests achieved stable travel between 50 to 150 yards, 25% partial success. 21 tests resulted in directional failure within 50 yards or immediate loss of control, 65.6% failure rate. 7 tests resulted in structural damage requiring unit reconstruction, 21.9% catastrophic failure. Loss rates for test units: 4 Mark I prototypes destroyed or damaged beyond repair during testing. 6 Mark II prototypes destroyed. 3 Mark III prototypes destroyed. All surviving units were ordered destroyed in June 1944 per classification protocols. Total program loss rate, 100%. Not a single Panjandrum prototype survived the war. Crew casualties, none. The Panjandrum was unmanned by design, specifically to avoid casualties. Personnel injuries during testing, 2 minor injuries from rocket fragments during Test 14, no serious injuries recorded. Animal casualties, 1 dog killed, January 15, 1944. Total program cost, £47,320 in development, testing, and materials through June 1944, equivalent to approximately £420,000 sterling in 2024 value. Cost per test, £1,478. Cost per successful test, defined as stable travel exceeding 150 yards, £15,773. Comparative analysis reveals the stark difference between the Panjandrum and the beach obstacle clearance systems that actually saw combat on D-Day. Sherman Crab Flail Tank, British modification of American M4 Sherman medium tank. Added rotating flail mechanism with 43 chains, each tipped with a steel ball weighing 5 pounds. Flail rotated at 140 RPM, detonating mines and clearing obstacles 10 feet wide. Weight, 33 tons including flail mechanism. Maximum speed, 15 miles per hour with flail deployed. Reliability, 85% operational rate on D-Day. Production, 287 units completed by June 1944. Combat effectiveness, cleared approximately 12,000 square yards of beach obstacles on June 6, with 22 units lost to enemy fire or mechanical failure. Survival rate, 92%. Churchill AVRE, Armored Vehicle Royal Engineers, British tank modified to carry petard spigot mortar, firing 40-pound high-explosive demolition charges. Range, 80 yards. Penetration, sufficient to breach 6 feet of reinforced concrete. Weight, 40 tons. Maximum speed, 8 miles per hour. Reliability, 78% operational rate on D-Day. Production, 180 units completed by June 1944. Combat effectiveness, destroyed approximately 80 German fortified positions on June 6, with 14 units lost to enemy fire. Survival rate, 92%. The philosophical difference was fundamental. British specialized armor accepted weight penalties for crew protection, mechanical reliability, and operational flexibility. The Panjandrum sacrificed everything: guidance, reliability, controllability for simplicity and unmanned operation. The specialized armor required trained crews but brought them home. The Panjandrum required no crews but couldn't hit its targets. Statistics tell the story. Sherman Crab production, 287 units, 250 survived D-Day. 87% remained operational throughout Normandy campaign. Panjandrum production, 13 units, 0 deployed, 0 survived. Sherman Crab development cost, approximately £12,000 per unit, including modification costs. Total program cost, $3.4 million.
Panjandrum development cost, £47,320 for 0 operational units. Yet the Panjandrum's cost-effectiveness emerged in unexpected metrics. German defensive preparation against rocket wheels, £180,000 in materials and labor. British intelligence estimates, 2,800 specialized barriers that could have been 450 concrete bunkers. Wehrlost engineering time, 112,000 man-hours diverted from other defenses. Return on deception investment, 380%,
achieved entirely by accident through documented failure of a weapon that could not be controlled. Lieutenant Nevil Shute Norway returned to civilian life after the war, resumed his writing career, and never publicly discussed the Panjandrum until official declassification in 1964. In a 1966 interview, Norway reflected, "We built something that looked terrifying, that generated tremendous noise and smoke, that appeared to be a serious weapon. It wasn't. But the appearance was sufficient. I spent 18 months trying to make it work as designed. I should have spent 18 minutes realizing it never would." Admiral Mountbatten understood this immediately. He saw the value in failure. Engineers rarely do. Captain Brian Kennett, chief engineer for the testing program, kept detailed technical notebooks throughout development. His final entry, dated June 8, 1944, reads, "Test 32 represents the culmination of every modification, every lesson learned, every engineering solution we could conceive. The device achieved 220 yards, 68% of required range, before losing control. This is the theoretical maximum performance achievable with available materials and propulsion technology. Further development would require technology that does not exist. Recommendation: terminate. We built the best possible Panjandrum. It is not good enough, and never will be." The test units destroyed in June 1944 disappeared completely. No museum holds a Panjandrum. No photographs exist of complete operational units except those taken during tests at Westward Ho Beach. The weapon exists now only in declassified documents, witness testimony, and the specialized barriers German engineers built along French beaches to stop a device that was never coming. January 15, 1944. Westward Ho Beach, Devon. Admiral Lord Louis Mountbatten watches smoke rising from the Panjandrum's final position 620 yards from launch, 280 yards from its intended target. The device sits motionless now, rockets exhausted, having terrorized everyone present while threatening no one it was designed to destroy. Engineers approach cautiously, confirming the test unit is safe, beginning recovery operations. The observation stands slowly empty as senior officers return to staff cars. Conversations hushed, nobody quite willing to articulate what they just witnessed. Mountbatten turns to Norway one final time before departing. "Lieutenant, your weapon has demonstrated exactly what was needed. Not what you intended to demonstrate, but what the situation required. Sometimes the most valuable thing an engineer can create is not something that works, but something that appears to work to those who most need to believe it works. Continue your tests. Document everything. Ensure photographs are available through appropriate channels. The Germans will draw their own conclusions." Norway never discovered whether Mountbatten planned this outcome from the beginning or improvised brilliantly in the moment. Post-war analysis suggests improvisation. The Panjandrum was genuinely intended as a combat weapon until testing revealed its fundamental unreliability. But Mountbatten's instantaneous reframing transformed catastrophic failure into strategic success, demonstrating the kind of adaptive thinking that defined Allied special operations throughout the war. The Panjandrum's journey from concept to cancellation reveals several enduring lessons about military innovation, engineering ambition, and the gap between theoretical capability and practical reliability. First, appearance of capability matters as much as actual capability in strategic deception. German intelligence photographed the tests, analyzed the specifications, and concluded Britain had developed a serious threat. Vorlacht engineers diverted resources to defend against that threat.
The deception required no elaborate planning, no careful orchestration, merely the documented existence of a development program that looked credible. Modern military planners exploit this principle routinely, maintaining research programs for weapons that may never deploy, specifically to force adversaries to invest in countermeasures, to spread defensive resources across multiple threats, to create uncertainty about actual capabilities. Second, reliable mediocrity defeats brilliant unpredictability in combat. The Sherman Crab flail tank was not revolutionary. It was a conventional tank with chains attached. But it worked 85% of the time, it brought crews home, and it cleared thousands of yards of obstacles on D-Day. The Panjandrum was revolutionary. Nothing like it had been attempted before. But it worked 9% of the time, it threatened friendly forces, and it never saw combat. Wars are won by systems that function reliably under stress, not by systems that promise revolutionary capability if only they can be made to work. Third, the willingness to abandon failing programs demonstrates strategic wisdom. British weapons development canceled the Panjandrum in June 1944, despite 18 months of investment, £47,000 in costs, and institutional pressure to produce results. This decision freed resources for systems that actually worked. The willingness to accept sunk costs, to acknowledge when engineering cannot overcome fundamental limitations, to redirect effort toward achievable goals, these are harder than continuing failed programs, but they are also more valuable. Fourth, human life has strategic value that transcends individual missions. The Panjandrum was designed specifically to avoid casualties. Unmanned delivery meant no crews at risk. But its uncontrollability meant it threatened everyone indiscriminately, including friendly forces. British specialized armor accepted significant weight penalties for crew protection. Armor plating, escape hatches, fire suppression systems that reduced combat effectiveness but increased survival rates. The Sherman Crab weighed 33 tons, much of that weight in protection systems. It survived. The Panjandrum weighed 8,400 pounds of offensive capability, with zero protection. It was destroyed in testing. The armies that protected their people won. The armies that treated people as expendable resources lost. The Atlantic Wall still stands in places, concrete bunkers weathered by 80 years of salt air, testament to German engineering and to the defensive works that made D-Day so costly. Scattered among those fortifications, if you know where to look, remain the specialized barriers Wehrmacht engineers installed in May 1944. Heavy logs angled seaward, positioned to stop rolling devices, defending against a threat that existed only in intelligence reports and British engineering failures. No Panjandrum ever rolled up those beaches. No rocket wheel ever smashed those concrete walls. The weapon that was supposed to revolutionize amphibious assault revolutionized nothing except German defensive planning. And even that revolution was accidental, unplanned, the byproduct of documented failure rather than deliberate deception. But in that accidental success lies a deeper truth about warfare, engineering, and the unpredictable ways that failure can serve victory. The Panjandrum was not poorly designed. It was brilliantly designed to achieve specific goals within specific constraints. Those goals simply could not be achieved with available technology. The constraints could not be overcome with available materials. And the engineering ambition that created the device could not force physics to cooperate with military necessity. The examination of the final test unit on June 2, 1944, provided the conclusive proof. The rocket mounting brackets showed stress fractures from repeated acceleration forces. The wheel framework showed warping from asymmetric thrust. The central drum showed weld failures from impact stress. The device had been pushed to its absolute limits across 32 tests, and its absolute limits were insufficient for combat deployment. Engineer Lieutenant Nevil Shute Norway learned what every military engineer eventually learns. Some problems have no solution. Some weapons cannot be made to work. And the hardest skill in engineering is knowing when to stop trying. Admiral Lord Louis Mountbatten learned what every strategic commander eventually learns. Victory comes from exploiting advantages wherever they appear, even in failure, even in weapons that threaten your own forces, even in engineering disasters that accidentally become deception operations. And the Germans learned what every military force eventually learns. Intelligence reports can be accurate and still mislead. Photographs can document reality and still deceive. And the most dangerous threats are sometimes the ones that never materialize. Because while you prepare for phantom weapons, real weapons find you unprepared. The Panjandrum chased British generals across a Devon beach on January 15, 1944, killed a photographer's dog, and nearly exploded with 1 ton of force in the midst of Allied high command. It never killed a German soldier. It never destroyed a German bunker. It never rolled up a French beach, in anger. But it made the Germans believe it would. And in war, making your enemy waste resources preparing for threats that don't exist is sometimes more valuable than the threats that do. The most uncontrollable weapon in the British arsenal became, through pure accident of circumstance and brilliant improvisation of command, one of the most effective deception operations of the Second World War. That single fact tells you everything you need to know about the gap between planning and reality in warfare, about the value of adaptive thinking over rigid doctrine, and about why the Allies won while building weapons that barely worked, because they knew when to abandon what didn't work, how to exploit every advantage, including failure, and that bringing soldiers home mattered more than building the perfect weapon. The Panjandrum never worked, but it succeeded anyway. And in that contradiction lies its entire legacy.